Welcome back. So today we're going to talk about L'Hopital's rule. This is the last lesson that we're going to do before test 3. Test 3 is going to be Friday. Cover everything since test 2. We'll review on Wednesday. And we're like so close to done. This week, next week, and the following week is when final exams start. I think we might have 1 class or 2 classes that week, but exams start that week. So that's it for our schedule. This last project is just a reflection project where you can give me some feedback about the course. It's not mathematical. Yeah, so I will give it to you the 11th. I don't know what day that is. And then it'll be due at the final exam. And I promise I won't look at it until after I have given you your final grades. Okay, so you can be honest. Okay, so today we're going to use L'Hopital's rule to evaluate certain kinds of limits. Brief history lesson about L'Hopital. This is all one long name. He was a French mathematician who wrote the first European textbook on calculus. But the quotes around wrote are necessary because virtually the entire textbook was plagiarized from notes made by another mathematician, Bernoulli. Okay. So L'Hopital had paid Bernoulli to tutor him in calculus because Bernoulli was only one of a handful of people who could understand the new subject, and Bernoulli sent L'Hopital a bunch of notes, and L'Hopital then published them. Okay. L'Hopital is his name. Yeah, it is the French word for hospital. Yeah, but it's his name. Yeah. Yeah. Okay, so his name lives on famously for L'Hopital's rule, but I just wanted to point out that it's really not his rule. Okay. So we're going to look at 2 limits. This is one of the limits from the questions of the day, and we're going to do this problem 2 different ways. Okay, so up until today, the way we would have addressed this is first thing you try to do is you plug in the number, right? You try to plug in the number. If you get an answer, if you can plug it in, then that's the answer, that's the limit, right? So let's see what happens if I plug 2 into this limit. I get 3 times 2 squared minus 2 minus 10, or 5 times 2 squared plus 3 times 2 minus 26. Okay, so that's 4 times 3 is 12, minus 2 is 10, 10 minus 10 is 0. 2 squared is 4, times 5 is 20. 20 plus 6 is 26, minus 26 is 0. All right, 0 over 0. What is that? It's undefined. Yeah, it's called an indeterminate form. Undefined, because you can't divide by 0. And there's sort of there's sort of conflicting rules in that fraction. Like 0 over anything is supposed to be 0, but anything over 0 is undefined. But any number over itself is supposed to be 1. So there's all these conflicting rules there, so we have to call that indeterminate. You can't tell what that is. Indeterminate, yep. Okay, so when we find an indeterminate form, what that means is that you have some more work to do. You have to do some algebra to try to see if you can simplify things before you plug the 2 in. Okay, so I'm going to try to factor and cancel. Okay, so I'm going to do the limit as x approaches 2. 3x squared minus x minus 10. It's going to factor. It's going to be a 3x and an x. And then 10, maybe 5 and 2. I put nope, switch that. 2 and 5, because that gives me a 6x and a 5x. I want the answer, the x to be negative, so I'll put a negative there and a positive there. So that gives me 3x squared minus 6x plus 5x minus 10. Good. All right, and then my denominator, 5x squared plus 3x minus 26. So I've got to have a 5x and an x to make 5x squared. Factors of 26. 13 and 2 are like the only ones because 13 is prime. So it's got to be 13 and 2. And I want them to sum to 3. So I think I'm going to put the 2 here and the 13 here because that gives me 10x and 13x. I want it to be positive 3. So that one's going to be negative and that one's going to be positive. All right, so that's nice because my x minus 2's cancel. And now if I plug 2 in there after I've done my canceling, I get 3 times 2 plus 5 over 5 times 2 plus 13. 6 plus 5 is 11. 5 times 2 is 10 plus 13 is 23. 11/23. So we already have done this before, right? Okay. So the new thing we're learning today is L'Hopital's rule. It's just another way of calculating this limit. Okay, so 0 over 0. That's the limit, right? The numerator is approaching 0 and the denominator is approaching 0 as x approaches 2. So where it ends up, where the limit ends up, depends on which one is going to 0 faster, right? If the numerator is going to 0 much faster than the denominator, then the whole fraction will go to 0, right? Because the denominator is shrinking really fast before the denominator gets to 0. If the denominator were going to 0 much faster than the numerator, the whole fraction would blow up to infinity, right? But they might like sort of strike a balance in how fast they go to 0. If they go at relatively the same rate, it might come out to 1 or some other constant, like 11/23. All right, what mathematical tool do we have that can tell us about how fast a function is changing? The derivative, yeah, derivatives can tell us how fast the numerator is going to 0, how fast the denominator is going to 0. So L'Hopital's rule says that I can take the limit as x approaches 2, take the derivative of the numerator and the derivative of the denominator, and it will be the same limit, okay, as the original function. So I'm not taking the derivative of the quotient, right? I'm not going to use the quotient rule here. I just want to know how fast the numerator is going to 0, so I take the derivative. How fast the denominator is going to 0, so I take its derivative. So I take each derivative separately, then plug in my 2. So my derivative of my numerator is going to be 6x minus 1. Derivative of the denominator is 10x plus 3. And once I've taken the derivative of the numerator and the denominator, now when I plug in 2, I get 6 times 2 minus 1 over 10 times 2 plus 3, which is 11/23. Same thing I got using factor and cancel. So this method is called L'Hopital's rule. If you have an indeterminate form of 0 over 0 or infinity over infinity, you can use L'Hopital's rule and you'll always get the same thing. All right, so let's look at another example. It's the exact same function, but now I want to know what happens as x goes to infinity instead of x going to 2. So I'm going to start by just saying what happens to my numerator as x goes to infinity. It's infinity. It's 3x squared, which means that both arms go up, right? Because it's even degree, positive leading coefficient. So my end behavior of the numerator is infinity. And the denominator, same thing, also infinity. Infinity over infinity is, again, an indeterminate form. The actual limit is going to depend on which one goes to infinity faster, right? If the numerator wins by a landslide, the whole fraction will go to infinity. If the numerator is getting bigger faster than the denominator, the fraction just grows. But if the denominator is getting bigger faster than the numerator, the fraction is going to shrink to 0. But they could strike some kind of balance and go to a constant somewhere in between 0 and infinity. So I could do my factor and cancel again, right? So, or I could use the result you learned in pre-calculus, right? Remember when you think about the end behavior of a rational function, we'd say, well, look at approximate, well, no, it's equal to. So if I'm going to let x go to infinity, I'm going to plug in the biggest x values I can think of. Imagine plugging in 1 million. What is 1 million squared? It's a big number. It's a 1 with 12 zeros after it. It's a big number, right? It's a million times bigger than a million, right? Because it's a million times a million. It's so much bigger than a million that when I do a million squared and do times 3, if I then just subtract a million, like if you think of it in dollars, if you have $1 million squared dollars and you lose $1 million, you're like, whatever, right? Same with $10. You lose $10, you're like, it's like in my couch cushions or something. So when x is really, really big, the only thing that matters are the leading terms in terms of what happens in the end behavior, right? Because x is really, really big. So I can just say 3x squared over 5x squared. You can cancel the x squareds and you get 3/5 is your limit. Is this familiar from pre-calc? You might have just memorized a rule, like when you're looking at a rational function, if the degree on top is the same as the degree on bottom, the horizontal asymptote, which is the end behavior, is the ratio of the leading coefficients. So let's see what happens if I apply L'Hopital's rule, right? Because L'Hopital's rule can be applied when you have infinity over infinity also. So this is going to be the limit as x goes to infinity. My derivative is 6x minus 1. It's the numerator. Derivative of the denominator is 10x plus 3. And my numerator as x goes to infinity goes to infinity. Denominator as x goes to infinity goes to infinity. Still an indeterminate form. So here's one of the great things about L'Hopital's rule. You can just do it again. Right? So this is the limit as x goes to infinity. As long as it still goes to an indeterminate form, you can take the derivative of the top and the bottom again. So this is 6 over 10. So the limit as x goes to infinity of a constant is just that constant. Why can you just do that? Because that's what. Because when I did the first derivative, it gave me another indeterminate form. And anytime you're trying to take a limit that comes out to an indeterminate form, you can apply L'Hopital's rule. So it's like a brand new problem. Like if I had started here and got infinity over infinity, L'Hopital's rule would say take the derivative of the top and the derivative of the bottom. See what you get. So you can do it as many times as you want until you get something that is no longer indeterminate. Yes. A number, yeah. So if your numerator is going to infinity, so let's say I had limit as x goes to infinity of 3x cubed over 5x squared, right? I could take the derivative of the top and the bottom, so I'd get 9x squared over 5x. Do it again because that still comes out to infinity over infinity. So you get 18x over 5. Now you get infinity over 5, right? What's infinity divided by 5? Infinity, yeah. So in this case, your limit is infinite. The end behavior of that rational function, it goes up to infinity. What if you ended up with 5 over infinity? Like if I flipped that fraction over, what would be 0? Yeah, in a fraction, if the numerator stays constant and the denominator blows up, right? Think 5 over 10, 5 over 100, 5 over 1,000, 5 over a million, getting closer and closer to 0. Good. All right, so the above technique works for general limits of indeterminate form if it looks like 0 over 0 or infinity over infinity. And it doesn't have to just be positive infinity. You can have negative infinities in there too.
So be positive over negative?
Yep. So the technique is called L'Hopital's rule. It says that if the numerator and the denominator both go to 0, you have a fraction, numerator and denominator are both going to 0, you can take the limit as x goes to that same value of f prime over g prime, and it will be the same. Like that will give you the answer. Same thing if the numerator and denominator are both going to infinity. You can just take the derivative of the numerator and the denominator and take that limit. All right, that's it. So you can try some.